Good afternoon, everyone. Today, we're going to start a new subject, right? Remember, we started and we covered in the first part of our lecture what closed system is, and we solved problems on pure substances, ideal gases by using first of all thermodynamics, reading tables, and etc. What everything was about on a closed system. Now we switch our focus to open system applications, okay? Open system, you will see, and I will explain in deep details. Open system covers closed system, but closed system is a specific case where you have a closed system, okay? You can treat closed system as an open system as long as you're consistent with your equations and your processes, okay? I will show you and I will explain, but you should know that open system covers everything. Okay, let's start. Well, let's say Saturday. Seven, right? 6 p.m. I will give you enough time to complete, all right? So in the exam, you had 85 minutes. And I also added 5 more minutes on it. So I will give you enough time, but you know what to expect now. Okay? All right. First law of thermodynamics for open systems. For closed systems, remember when we define closed system, what makes system closed was mass is not allowed, right, to the boundary. That was our condition. Closed system also called mass control, right? Mass, control mass. But in the open system, mass is allowed pass through boundaries. It's free to move. But on the other hand, volume is constant. But it's not the volume that we considered in the closed system case. Okay? I will explain that in a minute. So change okay. The closed system and open system. We had a system from state 1, state 2, and we were conducting those states with some processes. Right? And in the open system, we have inlet and outlet. Remember, mass is allowed to pass through the boundaries. Okay? And we conduct these states for inlet and outlet through some process. And closed system is also called Lagrange, and open system is Euler or control wall. General conservation equation. For any quantity conserved with respect to open system for some specified time interval, we may write the amount of quantity entering amount of quantity generated minus amount of quantity leaving equals amount of quantity accumulated in the system. So the amount of quantity entering my system plus amount of quantity generated inside the system minus amount of quantity leaving should be equal to amount of quantity accumulated at the end. Okay, and this can be applied to anything in life, including your bank account, right? Anything. Right? Amount of quantity entering, the money you put at the back, your bank account, right? Plus the interest amount generated minus amount that is leaving, meaning you're spending, right? Should be equal to whatever you have remaining. You can apply this to anything. All right, we can also write this we may also write the conservation equation in rate form. Okay. Rate of quantity entering plus rate of quantity generated minus rate of quantity leaving equals rate of quantity accumulated. Okay. As I said, this quantity in these equations, quantity in these equations or statements might be any property. Property that is conserved with respect to control volume. Electrical charge. Atoms, molecules, mass, momentum, energy, money, okay, etc. But mainly here we will be focusing on mass, momentum, energy. Mass is called, or continuity equation. Momentum, second law of thermodynamics, and energy is the first law of thermodynamics. Let's start with first one, mass. Conservation of mass for the controlled volume. Or open system. Let's say we have control volume looks like this. In, inlet, out. Consider this as a control volume. So if we go back to our statement bar here, right? Quantity entering plus quantity generated minus quantity leaving equals quantity accumulated, right? So let's apply this to here, right? This is our system method. So in this case, I'm doing conservation of mass. I'm doing conservation of mass, right? So the amount of mass entering system, right? Let's consider there's no generation in the system minus amount of mass exiting or out. You can use it, you can see it both, E or O equals amount of mass generated in the control volume. Let's write in the statement what this each term means, okay? The time rate of change of mass contained the control volume at time t. Okay. This is this one. So let's start backwards. Okay. The time rate of flow of mass in a gross inlet at time t, right? So we said there is no generation, zero, so we neglect that. But sometimes that is the case. You have a generation inside the system, right? Let's call it heat source for chemical reaction or electrical wave, right? Electromagnetic wave that generates some sort of an energy or momentum inside your system. But let's put that on a side now. Minus time rate of flow of mass out across exit or E at time t. Okay. This dm control volume over dt, this is basically what it means, mathematical way, okay, equals summation of inlets at a time interval, right, minus summation of outlets of mass, right? So in this case, we had one inlet and one outlet. Here, one inlet, one outlet. But it might be multiple inlet and multiple outlets, right? In that case, summation of inlet entering your system and summation of mass leaving your system. Okay. In this case, if we apply this to our schematic in our system, so dm control volume over dt will be m in minus m out, right? Or m exit, if you like to call it exit, right? Okay. All right. So dm control volume over dt, and that means flow rate flow. In this case, mass flow rate. Okay. Mass flow rate m dot of the matter entering or exiting a control volume can be obtained in terms of local properties by considering a small quantity of matter flowing with velocity v across an incremental area dA in a time interval delta t. Okay. Any questions so far? Okay. So what we are trying to do is showing you how open system is the general concept of a thermodynamic, right? So you can take this expression, statements, or equations and apply on a closed system. What would it be? M is whatever you have in a closed system, because there's no entering or leaving, right? And it's constantly closed. And you can apply this. M in is 0 and out is 0, for example. Ready? Okay. Okay. The amount of mass crossing dA is the incremental small area, right? Smaller, you can say. I would say integration, but it's dA, right? Incremental and small area that we are crossing during the time interval delta t, right? It's rho Vn EdA. Instantaneous rate of mass flow across the dA increment, just a small area, will be equal to rho Vn dA. If we integrate this over area, right, d and control volume over dt, which is dot, right, equals integration of rho Vn dA integrate over the area A. This is the case where mass passes through a specified area. For example, you can call it pi. Right? For cases, for example, where mass crosses the boundary only at specified area. EM control volume ET, if we take the integration over volume, for dV. The integration is over the volume at time t. So knowing this, right, we have E dt integration of rho dV equals summation the inlet area rho velocity passing through this infinitesimally small area, right, inlet minus summation of outlets area rho velocity passing through that area outlet. This is an integration form of mass rate. For steady state applications, steady state means there is no change in the mass in the control volume. Basically, the amount of accumulation is zero. or the M control volume over dt equals 0, in other words. If density and velocity are uniform across pipe, right, M be equal to rho VA or VA over the volume. I know my dm control volume over dt equals summation mass entering and exiting, right? For steady state problems, amount of mass entering the system equals the amount of mass exiting. Okay. Any questions? Yes.
Should we go back to page 3?
Right. Okay. Example. Everything is still same. We are still using tables. We are still using the same properties, same method. Everything is same. We're just going to apply that on a control volume instead of control mass, okay? By using all those equations and statements. Okay? For example, steam enters a steady flow device at 160 bar and 560 Celsius with a velocity of 80 meters per second. At the outlet, the fluid is a saturated vapor at 2 bar, and the area is 1,000 centimeters square. The flow rate is 1,000 kilogram per minute. Determine A, the inlet area in centimeters squared, and B, the outlet velocity, meter per second. Right. So what I have here is an open system. And I can tell from the problem statement, it has a one inlet and one outlet. Right? It doesn't have to specify that it has a one inlet or one outlet. Right? And I can understand that it has a one inlet and one outlet. So from there, right? For one inlet, one outlet. M in, M out. At the inlet, it says pressure is 160 bar, right? Temperature 560 Celsius. Velocity is 80 meter per second, right? And it's a steam. That's another information that I know. The inlet. Steam. Right? At the outlet, pressure is 20 or 2. It's 2 bar. Area is 1,000 centimeters square. And it is saturated vapor. Also given mass flow rate 1,000 kilogram per minute. That means for steady state system, M in equals M out. Remember, for steady state system, right, accumulation is 0. If accumulation is 0, we assume that the generation in the system is 0, but in equals out. Since I have one inlet and one outlet, they have to be equal, right? And in equals them out. So let's begin with looking at the tables. Okay. We need to read our properties from the table. If you want to double check, you can use your tables and see if you can see those properties. Okay? The inlet. Which table would you use? Why? All right, everybody understand why we're using? Okay, we're in the superheated vapor region because we exceeded the saturation temperature, right? At that specific pressure, which is 160 bar heat, which puts us in a superheated vapor. If you go to superheated table, like that temperature 560, right? At that pressure, you should have 160 bar, right? So if you find that pressure, go to 560 Celsius. If you don't have it, you need to interpret. Right? So what's your specific volume? Specific volume should be, right, table A4, right? 160 Celsius. The specific volume should be 0.02172 meter cubed per kilogram. I know my mass flow rate. I know my specific volume. I know my velocity. You can calculate my area. Remember, mass flow rate equals rho VA or V velocity times area over specific volume. Okay. So I know everything except area at the inlet, so I can calculate that. So for rho A or specific volume, okay, mass flow rate A1, you can either call it I, E, or O, or you can say 1, 2. All right? I'll call it 1 in this case. A1 equals mass flow rate times specific volume over velocity. And mass flow rate is 1,000 kilograms per minute.
Did you go for
Specific volume is 0.02172 meter cubed per kilogram. Okay. Velocity is 80 meters per second. But we need a unit conversion. Under centimeter a meter. And I need to convert minutes per second. Right? I have a minute. Area A1 will be 45.2 centimeters squared. At state 2, for outlet, the exit specific volume is 0.8857 meters cubed per kilogram. You can double check. We have a saturated vapor, the outlet, and you know the pressure. You can read it. Velocity at the outlet, using the same equation, mass flow rate equation, right? Mass flow rate equals area times density times velocity. I know everything except velocity at the outlet. Mass flow rate is 1,000 kilogram per minute. Specific volume is 0.8857 meter cubed per kilogram. Area is 1,000 centimeter square. But they don't cancel out, so we had to do the unit conversion. Centimeter meter per 60 seconds per minute. Velocity will be 147.6 meter per second. You can check my answers. It wasn't too bad, right? And make sure you know how to read those values from the table. Try it by yourself. Okay. All right. Conservation of energy for control volume. Or open system. Okay. For an open system, with one inlet, one outlet, mass flow rate entering the system, mass flow rate the exit. What accumulates inside the system is mass plus energy. What differs open system from a closed system, we have an additional mass you might have, right? So and also we have elevation difference. Elevation at the exits and elevation at the inlet. Remember, we were neglecting potential energy, but we have a potential energy because of elevation difference. It might be negligible, it might be small compared to other terms in the problem, but we should be aware of that. We have a potential energy. And we have also kinetic energy because of velocity, because it's moving, right? And can live with a certain velocity, with a certain speed, right? Okay. Let's mention this as well. We have a work interaction, heat interaction, sets. In or out, in or out. So by just looking at this, right, specific schematic, right, you can write the energy change inside the system, right, that interval time change, right, equals amount of heat entering the system minus work out, right, plus the amount of mass entering, and it carries an energy with itself. So internal energy plus what, kinetic energy plus potential energy. Minus mass flow rate at the exit, internal energy at the exit, plus velocity at the exit, kinetic energy, plus G gravity times elevation. Okay. Yes.
Actually, no, that's you. That very last one at the end of those graphics. Right?
Yeah. E to the exit. Okay. So remember this, each term Q and W has their own subtitles, right? Q in, Q out, work on, work by. Right? That's complete those. So Q in plus work on, and these are all in rate form, plus mass or energy interaction or energy introduced into the system. E in, I call everything in the big parentheses E, right? U plus V squared over 2 plus GZ, I call all of it an E. E. Plus 0, there is no generation in the system. If there's a generation in the system, it will be this part. Minus Q out minus work by minus summation of work out through mass. Summation of mass times energy out should be equal to energy accumulation inside the control volume. VE control volume over VT. And we have work that crossing boundary one form of work that must always be present when mass crosses the boundary. And this is called the boundary work. Boundary work is done by mass, caused by mass, by entering or leaving the system. Okay? Of the mass entering or leaving. So we will define the work into this boundary work, and also everything else would be called shock. Shock work. So I have two works here. One is caused by mass moving through my boundaries, and everything else is a shock work. The work you know is shock work. Right? The work we have been calculating for both systems, shock work actually here. And we have an additional work caused by mass passing through the boundary. It's also called boundary work. Okay, so work with work boundary plus work shaft. So work boundary caused by mass passing the boundary can be demonstrated, right? Work. Let's put it this way. Boundary work of mass crossing boundary it can be demonstrated. Work boundary equals PV or MPV. So V here is the volume, meter cubes, if you look. But also, work boundary at a rate form will be pressure times volumetric flow rate, okay? Meter cube per second, if you look. Therefore, work on or work by will be equal to work shaft plus mass flow rate pressure times specific volume, right? Which is boundary work, right? Okay. If we introduce this new term to our energy equation up here, let's see what happens. Okay. Putting this into energy equation. So Qn plus work shaft on plus summation of mass flow rate E in, pressure in, V in, right? Minus Q out minus work shaft by minus summation of workflow rate, the outlet, right? And out, I call it exit before, out. Specific energy at the outlet plus pressure at the outlet times specific volume, the outlet, equal to energy accumulation inside the control volume. So this E, right? I just call this E, and I have one here. What was it? It's a stored energy. Remember stored energy in the flow system? It's the same stored energy, but in the specific form. It's small e, right? So it's a specific form. That E is equal, remember, U plus kinetic energy plus potential energy, right? So the stored energy in this case, stored energy term crossing the boundary will be U plus PV plus kinetic energy plus potential energy. Remember this? What is it? Enthalpy, right? So it will be, if we recall the definition, enthalpy is U plus PV. So this equation I have will be Q in plus work shaft on plus summation of mass flow rate inlet H plus potential energy inlet plus potential energy inlet minus Q out minus work shaft by minus summation the outlet flow rate at the outlet H out plus kinetic energy the outlet plus potential energy at the outlet will be equal to energy accumulation inside the control wall. Okay. Okay. We can stop here for today. continue on Tuesday. So please make sure you prepare yourself for Saturday. Okay? And let me know if you have any questions, please.